Similar to the imaginary.
It was the imaginary.
No.
It should be the imaginary.
Oh, yeah, because on the diagonal, they alternate.
Oh, yeah.
So you have to rearrange it.
Well, it's not exactly.
I know, you have to rearrange it. But once you rearrange the set, the imaginary and the modulo 5 are the same. Right? And that's an isomorphology that I don't think anyone would expect.
But
I feel probably the same, I feel the same, more quality, where you can more than
here's the thing, this one like thing one day.
Yeah, but like that, we check like the order of the key, and then like. the problem,
So in theory, we could pick like any module.
No. You have to pick carefully. Right? Because your set, if you want it to be finite, has to have relationships, right? So the fact that you have a modulo, let's say 8, with these 4 numbers, there is a deeper relationship underneath the fact that that is a set, right? So when we talk about group theory, when we talk about the rules necessary to understand group theory, it's not just saying any numbers. It's any numbers under an operation which has those 5 properties. And those 5 properties relate to something unique, mathematical underneath the surface, something that's not obvious, right? But the interesting part about an isomorphology between any 2 groups is it speaks to the underlying mathematics, right? Okay. So of course you could take that 4, the set of 4 elements in it, and you could relate it to another 4 element set, and it might have the same characteristics, right? It might send you from this thing to the other, right? So for example, we did one of them where it's like A, B, C, D, right? And then we saw the relationship between A, B, C, and D below. Those don't necessarily even need to be numbers. Does that make sense? Okay, so in preparing for today's class, I decided to sort of split it because I looked at some of the applications. And really to do some of the applications well, we could talk about what is called representation theory, which would be when we were talking earlier about, molecules. When we were talking about molecules, we were talking about the ways that we can understand how they're represented. Representation theory gets a little bit into that in more detail as an application of group theory. One of the more common uses of group theory is when you apply it to quantum mechanics. But you haven't taken quantum mechanics, is that right, Sarah? You haven't taken quantum mechanics. And you haven't, okay.
So, yes.
Okay, so that'll be less fun for you. Particle physics in particular is very interesting because you can talk about it in the context of how we understand the relationship between elementary particles. So I don't know if you've ever seen that before. Have you ever seen that relationship? Do you know what the elementary particles are?
Like
Kind of like standard model.
Yeah, leptons and hadrons, you know what they are?
We talked a little bit about it in Woodley's class.
We talked a little about it in modern as well, and it has like a little chart.
Yeah.
And then there's another one, and it's like a his photon, a proton, and an electron.
And they all have different masses and spins and stuff.
Yeah, right. So they look like this, right?
Yeah.
And so they always have this structure. So let's just talk about quarks for 1 second. And this, we're not going to go into detail here, so this is all going to be off the cuff. So what are the 2 quarks that we care the most about?
Up and down.
Up and down. Which one goes where?
One goes up, one goes down.
Anything else?
What?
No, that'd be
Oh,
funny though.
there's charm and there's what is it?
There's charm and there's strange.
Charm and strange.
Top and
Ow.
bottom.
Oh, okay, top and bottom.
Yeah, I know.
Flying.
I swear to God, look it up right now. Let's verify, because I'm pretty sure this is correct. So mass goes like this. Okay. increasing mass goes to the right. And there's a relationship here between the charges. What's the charge of the up quark?
+1.
No, they never have full charge.
Oh,
What's that?
it's like 2/3,
How many quarks do you need to make a particle?
3.
Oh, so
I
we
couldn't
did work
read
on
it
1/3.
up in here, I wouldn't read you the charge, it's really boring.
Oh, no, I just wanted to make sure this is right. Yeah, top bottom's on the.
It looks like 2 over 3 charge, but I can't tell.
Yeah, so sorry, that's getting away from what I was trying to say, or getting ahead of what I was trying to say. So, so the charges here, whenever you think about a particle, so let's say this is a proton. And it is charged 1. It's actually 3 quarks,
2 up, 1 down.
right? So I think this is 2/3 here. And this is minus 1/3. So you would have 2 ups, which contribute how much?
4/3.
4/3. And then you subtract off down, which contributes minus 1/3. So that gives you your proton. And similarly, you'd have over here a neutron, which has what charge? 0 charge, right? So what's that?
So 1 up and 2 downs.
Yeah, 1 up, 2 down.
2/3.
That's weird.
All right. Okay, so first you're like, that's weird, right? Okay, that's very strange. It gets weirder,
Oh,
okay? So there are properties in here about spins.
yes.
So the spin of these is really important. The structure here having 6 particles, you say, oh, that's funny, okay. There's basically 2 that you see in every single part of the day. Why are there more? Right, that's a strange thing. That's just the quarks. Okay, but there are more things in the standard model.
Leptons.
Leptons, what do those look like?
There's 3 that have the word neutrino, but I'm just reading it off from here right now.
That's okay. So leptons,
Neutrinos, yeah.
leptons are counterparts. Okay.
Okay.
And the one that you know the best is the,
Like,
right, so where does that go?
Uh,
So the electron actually is a lepton. And this is a point particle in the same way that quarks are a point particle. So a proton has a physical size, but these do not. These are our elementary particles. Okay, how do you go after the leptons?
the end of the rainbow.
No, sorry, how does this structure?
you mean like, oh, it looks like the top is -1 and the bottom is 0.
Right, but do you remember what the tops are? Someone who's not looking at, someone who's not looking at the thing?
I
It's
just.
just where like the.
I know there's 3 neutrinos.
There's 3 neutrinos, and the 3 neutrinos sit,
I know they
I mean, you can verify, right?
they like change as they move or something like that.
Yeah, they sit here.
Okay.
So this is the electron neutrino. And then you have tau, and you
Tau.
have the muon,
Mu.
right?
You have the flip.
I haven't seen, I was having fun. You can tell that I don't do particle physics every day.
No, okay.
Okay, and then you have the muon neutrino and the tau neutrino. And yes, to your point, this one, weirdly enough, allows you to cycle through masses, so neutrinos sometimes just change their mass. Fucking knows. These ones up here all have charge what?
1 or -1.
I hope so, right? Yeah, so they all have charge -1. Do these have charge?
No, they're not.
They don't
Exactly, and
interact.
they're very weakly interactive, right? Okay. So it's kind of weird that there's also, 6 of those particles, you'd be like, well, that's strange. But mass also increases in this direction. So that's weird too, right? Okay, so the stuff that makes up matter. The stuff that makes up the electric part of what we think of electrons, These both have, you don't have to write any of this down, guys. This is not gonna tell, okay, alright. You're having a great time, right?
Yeah,
Yeah.
that's why I wanted to do that.
Okay, so it turns out that there are I'm gonna say this improperly now.
Morphic?
By some,
There are isomorphic groups here that we can relate the standard particles to. And these are called the special unitary groups. I believe they're special unitary group 6. But verify that later outside of class when it'll be less embarrassing. Okay, so you think to yourself, well, that's pretty weird that there are 6 of these things too, okay? What about the force carriers? Do we know what we mean by force carriers?
I've heard a little bit about it,
like
one of them,
You can pull it up right now.
the boson?
Yeah,
The
so-
mass? Is mass?
So you get,
which I heard during class with galaxy stuff, that the Higgs boson might somehow be related to gravity.
yes, well, Higgs boson is responsible for gravity. In fact, but it's alone. And there is reason to believe that there are larger Higgs bosons because everything that we see in the boson group goes like 6. So if you look at the bosons really quickly, you have the bosons up?
There's 4 in a row and 2 of them say boson and then 2 of them say gluon and photon.
Okay, so let me see if I can draw this properly, because it's important, right? Yeah, so I won't draw it in this suggestive manner.
Oh, okay, yeah, it's kind of.
Let me just draw it separately. Let me just show you what the things that hold our world together are. So what's the first one?
Gluon.
Oh, the gluon.
So what does the gluon do? Well, the gluon is the force carrier, the thing that is responsible for holding quarks together. Sometimes we call this the color force. And we only call it the color force because people in the 70s, when they discovered quarks, it was the 70s. So they called the individual flavors, the individual types
They were all high.
of quarks, flavors. Does that make any sense? No, but it turns out that you need all 3, 1, 2, 3, in order for the color to be white. Does that make sense?
All 3 what?
You need 3 quarks. You will never, ever, ever find a quark on its own. Okay, you only find them in groups of 3. So in everything that we can create, everything that is matter,
You don't need 3 different types, you need 3 of them?
3 of them, yeah.
Okay.
Yeah, and you can make weirdo shit, right? You can make mesons and all sorts of like fucked up things with a bunch of quarks, but they always need to be in 3.
Mm.
And the force responsible for that is the gluon or the color force. Okay. Next one. I didn't spell that right.
Photon.
Yeah.
What's that?
Photon.
Okay, the photon, that's interesting. What does the photon do?
Electromagnetic.
The photon is the electromagnetic force carrier. Because remember, for those who took EM2, we found out that there is actually no difference between a magnetic field and an electric field, right? They are the same forces. They're just viewed through different perspectives. If you're moving near the speed of light, electric fields can become magnetic fields, and magnetic fields can become electric fields if you're not moving, right? Right?
Yeah.
Okay, next.
Z boson.
Okay, Z boson. Let's see if I remember what this one. There's one after this. What's the one after this?
W boson.
W boson. Yeah, so this is the weak boson and the strong boson.
So that's to do with holding together electrons and protons?
Yeah, this one, I believe this is the weak boson and
It's
this
the
one,
weak force.
this one allows you to change your, so for example, okay. Here you have a neutron. Here you have a proton. You can allow one of these quarks to change. Now, which one of these would you have to change to become a proton? Sorry, a neutron.
Of course, right now.
Which one?
Of course,
Up or down?
Yeah, so this guy here, up can become a down, but can only do so through the W force, the electroweak force. As it turns out, this is actually related to the electromagnetic force.
Oh, it is.
Yeah, so typically we talk about these in terms of the electroweak force. They're part of the same group. I'm not gonna write these in because I don't wanna write anything wrong on the board. So
So
this,
does Z have to do with the gluon because it holds stuff together?
yeah, I believe it has to do, Well, hold on. No, the Z has to do with the, excess color force. One of them is the excess color force, so that is the fact that, these particles here, right, not only are they attracted to one another, they also, if you have two protons, they can bind near one another because they have a distance away from one another, they can hold on to other quarks.
Hmm.
Does that make sense? No?
No, I just tried to Google it. They
The
were-
strong, that's the strong force that holds them together, right? That's the,
Well, okay, so strong force is, yes, yes, in the shortest sense of the word.
Yeah, there are a lot of like weird hippie words with all this stuff. Sunshine, at certain websites, it's sunshine and stardust.
Yeah.
That's
Yeah, no, they really did this in the 70s and 80s. So the reason that you have, for example, right, these things have positive charge and this has negative charge. And yet, what happens here? This whole thing stays together. And it stays together locked, really tight. Because the strong force is strong, much stronger by orders of magnitude than the electronic force, right? Or the electromagnetic force. Okay. So that's 4 of the force carriers. What's the name of the Z and the W?
boson.
Z boson and W boson.
Really? So where?
Well, yeah, that's what I got in this picture.
And what's the last one?
Higgs.
Okay, so what's the Higgs do?
That gives mass to particles.
Yeah, this is the gravitational force. Okay. You see anything weird?
It's not 6.
It's not 6. So there are reasons for people to believe, based on the I'm doing this wrong again. How do you say it?
Isomorphic.
Isomorphisms. Because of the isomorphisms in the groups and the ways that these individual products relate to one another, people believe that there may be a larger Higgs boson. Does that make sense?
Yeah.
When we look at things like dark matter, and we're looking out into the universe, one of the explanations that people use, there's 2. One is called WIMPs and one is called machos. WIMPs are the weakly interacting massive particles. Weakly interacting means weakly interacting with the photon, because that's the only thing that we can use to probe it. So it interacts strongly with the Higgs boson, but it interacts very weakly with the photon,
Hmm.
right? So there could be particles over here, more massive inside. Right, it's like there could be more leptons, but we don't think there are. And there could be more force carriers. Now, these just affect the way that the force is carried. This is not a new force. So when you hear people talk about grand unified theories, that is to say, all of these forces are one and the same, it's because we started off by realizing that electronic interactions and magnetic interactions were actually the same force. And then we realized that they were related to the weak force, and then we really realized they were related to the strong force. So suddenly you have 4 fundamental forces, and 3 of them are already linked. So we have been trying for years, not we, I haven't done it.
Oh,
That shit. But scientists in particular have been trying to take this last force, which is the Higgs boson, and find a unified theory, right? Because we think that that's probably what exists. If all 3 of them are related and this one's just, the odd one out, that would be pretty strange.
Are all
Cons-
4 of them related or just 3?
The 4 fundamental forces. So the 3 fundamental forces.
strong force, the
The
weak
4
force,
particles are.
electromagnetic force,
These
and
are-
gravitation.
There are more particles here than forces.
Yeah, but all those particles are related.
Yes, this one is related to this one.
Yeah.
In the way that the force particles interact. So what I mean by related is that, like, when you guys study quantum field theory, if you study quantum field theory, and especially like quantum chromodynamics,
Yeah.
what you're talking about is the interaction between the fields that hold all of the particles. So the particles are interacting with one another by sending photons back and forth. Okay, so that's how you communicate electromagnetic attraction, photons. Okay, that's a little weird, but I promise you'll get there. You'll be like, huh, that's a strange thing that I just learned. Okay, so the quantum field theory, the mathematics permits interactions between these objects, right? There's obviously a connection because one of them changes the very charge itself. So there's a deep connection between charge and electromagnetism, which you already understood. This charge is moving, changes the electric field, right?
Okay, were you talking also like the weak force of like particles stay?
Yeah, yeah, that, or a particle getting absorbed, right? So for example, I can absorb a neutrino, right, and spit out a positron. Right?
Okay, that's what it, because the neutrinos do change particles occasionally then?
Yeah, they're very weakly interacting, but it's possible.
Okay,
So this is a version of why group theory is interesting. If you love particle physics, start reading group theory now. Because there are some fucking weird things that you're like, why are they connected? And they speak to a deeper, I mean, mathematics is really unique, right? So generally I'm like, well, just let the computer do it, blah, blah, blah. But there's really something that is surprising about nature. That when you look around, right? For example, you find things like the golden ratio. That just exists in nature, like all over the place, in living things. Why? Why is the exponential so fucking ubiquitous? It shows up all the time. Why? Right? There are questions that as you begin to ask yourself, why is it that mathematics does such a good job at representing nature? Suddenly you find that perhaps mathematics is the language in which nature was actually written. And when you see special groups like this, you become even more convinced of it. Because you're like, okay, if I know these things here and the way that they're related, I can predict the properties of things that I haven't found yet. Does that make sense? Yeah, it's weird, right? Okay. So that's an application that we won't get into here today.
Okay.
I know. Okay, but we could do like a particle physics class next semester or something.
Partisan.
Already signed up for classes. All right, well, maybe we'll just do it over this summer. Like
Yeah, what classes should we
we
take?
do like a 1-unit seminar.
What
Or
class?
we could just all Zoom each other. and drink tea.
Drink tea?
Oh, yeah, that sounds great.
No. No, because then you won't do the homework.
Yeah.
And there's no homework.
There has to be homework. You can't,
No,
the
it's not
problem with,
class, we're just hanging out.
we're just saying that. So I'm just sitting up there talking about stuff that I barely understand.
Yeah,
For
we
sure,
can.
you know.
You know, like every other week. All right.
Yeah.
Like, for Easter.
All right. Excuse me?
We can have density meetings.
No, I don't trust other people.
Okay.
Okay. So sorry, that was just like a
Oh, big picture.
appetizer, like a little
Okay, oh.
taster of what the fun of group theory is. Yeah, one of those tea sandwiches, little cucumber ones. We could do that actually. I would be down for that. Okay. So I'll just talk a little bit more about the actual groups that exist and some of the weird ones. We saw the example of the triangles before that. But before we jump into that one, I want to talk about the homework. Because I've had a lot of people come at me. And they're like, what the fuck is happening? Okay, so I have this. Okay. Okay, so one of the things that we want to remember, right, is that that's X. That's the
Talking about homework done?
all of the homework.
Oh,
Oh, all the homework.
The complex analysis homework.
Yeah.
We're just gonna talk about the complex analysis homework for like 5 seconds,
Oh, yeah, no,
maybe a few minutes, and then we'll move on.
okay,
There's only homework done.
That's homework 8, right?
8 and 9,
Oh, okay.
yeah.
But in contour integral land, I mean, I basically just want to talk to you about the importance or the power of this tool. Because I know it's happening sort of later in the semester, so maybe you're not seeing as many of the applications.
It definitely kind of moving fast through it, so I'm kind of like,
Yeah.
whoa.
Okay, so here's your real one. Right? That's the world we tend to live in. It's not the world that we exclusively live in. And as you get into quantum mechanics, you'll see, Everything is fucking complex conjugates and raw and ket notation. Okay. And so here's your IY, right? And so the idea of working in this space was that, for example, with contour integrals, we could relate the real parts of equations to their complex counterparts. I don't want to say the word incorrectly here, but we could say that there is some f of z such that the real part of it equals some function of x.
Yeah,
Okay. And similarly, you can integrate them and you can find out interesting properties of them by taking advantage of the fact that there are some rules about analytic functions in the complex space, right? Right? Okay. So the first one here, these are only going to be pictures today, okay? Because you've seen the proofs. I don't need to do them anymore. Right?
yeah.
Okay. Let's see one. Let's see two.
Those points are singularities, or those points are,
These are points. This is a B. This is A. Okay. If A and B are not singularities, there's no singularities in there, and f of z is analytic in that region. How are C1, the integral of f of z1 related to integral
equal to 0?
the true?
Yeah. It's all analytic everywhere, yeah.
Yeah.
Should be 0.
Okay, so what does that mean about each one of them individually?
They equal each other, but negative.
But negative. Good. Okay, now what happens if I do this? I put a pole there.
It equals
Now
the
you gotta
residue.
use the residue theorem.
Good. Okay, so let's relate a residue here. So how do I write that here? Just write
Like,
2 by I,
Plus f of the residue.
not plus.
time.
Oh, no, times, that's what it is.
But we just do residue at some point, and let's
Oh.
call it, residue 1 or something.
Residue.
Okay. And it would be the sum, so you could, if you wanted to, you can do brackets. I'm not gonna do that here. Okay, so what was the fucking point? Why did I do that?
Because it's the same equation, it's just do with different, the end values, they're different.
Sure, but who gives a shit, right? Like, if I do this, right? And the first one was 0, and these two paths were equal, who gives a shit, right? Why would I even care? To go back one step, remove the singularity, who cares that the two paths integrating for this? Why is that helpful?
Because one path is easier than the other to integrate.
Yes, that is exactly why. One path is easier than the other to integrate. Okay? And we get to choose the paths,
Oh, okay.
right? So I showed earlier, remember we had this example where we went around in a big semicircle and went through the origin, and I let that thing get really big. And I said, I can approximate the integral here as long as I draw this semicircle. I drew the semicircle, right? Like I got to decide where the integral went and then relate it to these other parts. If there's a pole, then I draw something slightly different, right? So the first thing we do is we look at where is the function analytic and how. And we take advantage of being able to draw our own contours as we want to. Okay. So this one here, right? Let's say this top half somehow is harder than the bottom half. I don't know. It's a fucked up bottom. But let's say somehow the bottom half is the easier one, right? Then I can still use this relationship because all I have to do is move this over, right? Make sense? Okay, let's do one more. And then we're gonna really get into the important stuff. Alright. I drew 9 common contours. Some of them you'll use in the homework. Some of them you'll use the rest of your life. What's the one that you're using?
The
The,
one that we used that you showed me in the lot note?
the Z equals R E to the I theta. You're talking about?
You're saying words. I want contours.
Just,
Contours. Shapes.
oh,
There's no,
circles,
no math today.
okay, just,
Well, I mean, for right now.
I mean, the circle's the easiest one. and I'm
Circles,
like,
okay, so let's start with this circle.
Yeah,
Okay, so let's start with the circle. This is some point R. Right? That's okay. What?
Nothing big.
You said it's an ellipse?
that's wrong.
Okay. So this one here, I would think of as number 3, right?
Okay.
And we saw a lot of different iterations of this. So we saw a version of this where I stop here at another point, minus R, and then I head back this way,
Yeah,
right? Okay. You can always, of course, use either one of these. What was the reason that I used this big circle? You guys remember what the example was?
1 over Z.
1 over Z.
I know, let me see.
Okay. So 1 over Z does what at the origin?
Has a singularity.
Singularity.
Yeah, interesting. So there's a pole right here. Right? So I can do a lot of interesting things here, right? I can figure out what the value of different integrals are. This integral path, right, starts here, goes all the way around. It's not going to tell us anything about the real line. Right? So there's no integration along the real line unless, of course, I put one of the integral paths along the real line. This will tell us something specific about 1 over Z. Lets us calculate the value of the singularity, right? But if I want to, for example, let's look at a different one. If I want to travel along this path,
Okay,
Right.
the real line.
now I travel along the real line. And so I could, for example, look at the different paths. Let's call this one C1, let's call this C2, let's call this C3, and let's call this C4. Now, what am I really doing here is I'm integrating whatever the function is along all of them, right? Okay, so what is C1? Well, I shouldn't do a closed path. C1 f of,
Z.
is it though?
X.
It is f of x, right?
Oh, okay, it's on the real line.
It's on the real line, right? Plus,
Integral C2 f of x.
okay, good. So now we get it, right? So this is the reason why we're relating these different parts. Now, in practice, this is your f of z, but it's being evaluated on the real line,
Where the
Right.
rest is 0.
where the y is 0, right? So in practice, you can, if you want to be exactly perfect, you can just say,
Very pretty.
what do you mean?
It's been nice to have all the, yeah.
Oh.
So that's how you would write it, right?
Okay, I get what you're saying. I
Don't look so upset, folks.
was like, oh, look at the knife, but I was like.
This is a perfectly fine way to write it, right? You're applying, don't get mad.
No, I wasn't mad.
No, I wouldn't
like-
buy you. So each one of them contributes something different, right? And let's ignore for a moment that this is the f of z that has the pole in it. Okay, so let's imagine there's no pole inside. So what's that equal to? 0. Right? So depending on the function itself, you can make arguments, right? So you could make an argument about whether or not the function is symmetric. Because if the function is symmetric, then this contribution and this contribution have to be equal, right?
Oh, cause like even functions, they're gonna,
If the function is not necessarily, well, we wanna be careful with the words even versus symmetric, right? Are the values that I'm getting over here adding to the integral in the same way that they're adding here? Because if they are, right, then C1 plus C2 could go from minus infinity to infinity could be equal to 2 times 0 to infinity, right? Or similarly, 2 times minus infinity to 0. Right? That's the idea of symmetry. Make sense?
yeah.
Okay. And notice I'm being very fast and loose.
No,
I didn't write
yeah,
the
yeah.
functions in here at all. But this is the idea of how we can relate these different parts of the integral. So once we say, okay, well, these two pieces contribute this, well, it must be either equal and opposite to these ones, for example. Right? Okay. So that's one version. Questions about this number? Okay. All right, let's have some more fun with numbers. So still leaving off any, there's no isolarity. Oh my
There's
God.
no holes.
There's no poles or singularities. So let's draw another fun one. You're gonna love this one. Okay.
Okay, so that'd just be,
That's great.
F of Y?
What do you do?
It would be, it doesn't have a real component?
Yeah, so when you go down here, that could be evaluated as your imaginary term. Right.
Okay.
So let's say you have some function, right, that looks like the imaginary one. Right? Now you know that it's just related to this one here plus this one. And if, for example, you are allowed to let this thing R get very large, let's say I went out to infinity, and the value at infinity went to 0, then what would the contribution of the integral of C3 be? 0. And this would relate the real and the imaginary parts of the integral. Right? Now you don't always get so lucky. So this only works in specific contexts. What I'm trying to demonstrate here is that choosing things based on the values of your f of z and what you want to do with the integral means that you have to choose the contour properly. Right? So sometimes you don't want to evaluate it at infinity because the fucking function goes to infinity, right? That's useless. But maybe you want to evaluate it along a little contour here, right? To see what it does. Makes sense. Okay, let's try one more thing. Yolanda is on now, I'm going with this one. Well, I don't have to do power 4, but there's another one. Here's C2, 3, and here's C1. Right? So I can travel any amount of that circle I want. I can do the whole circle and come back to where I started. I can do the half circle. We saw some great applications of the half circle. I can do the quarter circle, and I can relate part. And similarly, I could always do something like this, right? I could go up, over, and back down. That also is totally valid, depending on what I want. Okay, this one is useful though for your homework. You remember why?
Yeah, and well, to be honest, I was having a hard time, on the problem one, it seemed like two different questions. It
Yeah.
seemed like the first part is like one question, and the second part is like a second question, it's like two different proofs.
No.
I was confused, I was like, what the hell is happening?
It's this question. This is the question. Okay, and the question, the meat of the question, the most important part of the question is thinking about how these three pieces of the contour relate to one another. So when I ask you questions about whether it's analytic, I don't give a shit if the function's analytic. I'm asking you to think about what is going on in the real space. And the question I'm really asking is,
I guess what's
Yeah, no, cause,
hold on, let me finish it. What did you say?
what's the length of C2 if that's on the real space?
Sure, but when I ask, is it analytic? What am I asking about?
Does it blow up?
Okay, another way of saying that is, are there poles or singularities? Are there poles or singularities? Why is that important? To contour integration,
Cause you have to go around them.
or
Does it equal zero or something else?
because you couldn't get it to equal zero if you do go around them, or you have to take them into account and provide their residual.
The residual, yeah.
Yeah, there's, I don't necessarily care, I just need to know if they exist. We have techniques for both. We can go around them, and I'll show you a bunch of different techniques for going around them. Or we can just,
Add the-
not include them. Or we can add their residues if we can find the residues, but I didn't really teach you how to find residues good, so, I'm trying to give you the contour integration part, which is the valuable part. So this section here, if there's no poles inside, then the pole contour is equal to. There you go, right? So now you have a relationship between the thing that you want and the thing that you can calculate, and believe it or not, you can calculate that C1 pretty easily. Come on now, don't be rude.
Well, it should be the same as C2, I mean.
Nope.
No.
You'll see. Do the math, do the math, I promise you, it is not as bad as it looks.
Well,
Okay, all right, so you saw some semicircles. Let's do some more. So we saw. I guess we saw a bunch of these semicircles. All right, let's do some poles. And this is the one that looks like a little person like peeking over the bed.
Oh, it reminds me of that one thing, I don't know if it's World War I or World War II, but they drew on like every take and like
Oh,
the first
Phil.
beat.
Oh, it was Kilroy was here.
Oh, that's
It's literally like that face with like a little nose.
Yeah, like
on
Sprinkles
it.
nose.
embarrassed.
I don't know,
No,
like a droopy nose, like
like
a
Sprinkles.
teardrop nose.
Okay, all right, I'm not gonna attempt to do my art skills, this is already pushing you today. Okay, this one looks like soon. You know soon? Soon. You don't know this meme?
like it's coming soon?
You know,
What's coming soon?
Look at those words up outside of class, you'll see. Because we're not doing memes in class today. We can do particle physics in class, but we're not doing.
Oh, I see it.
Okay,
Okay,
you see it?
so this one, you do the,
You got it?
you would just add both the residues?
Yeah, right?
Yeah, 'cause that's.
So now, am I going around the residues? Yes. Okay, so I said this was possible, right? And there's of course, some mathematical things that we have to do here. So we would break it up into, there's this big piece here, right? And we're going this way, and then we're going to go around this thing, and then we go this way, and we go around this thing, and we go this way. And we saw that we could take advantage of like this. Right? So when we did this for the example, where I said, well, you shouldn't have a pole along the contour. But we said, well, we can just take off the value of the contour here by imagining a different contour that is closed around here. Right? You remember this? So if we imagine this piece here contributes what?
The 2 pi I equals the residue, or times the residue.
2 pi I res, right? Then we can make that thing here. We can just say, well, it's half of it, right? And we can have the value for this thing. Even though it doesn't enclose that.
Oh, you're saying we drew, sorry, I didn't hear the last part, you drew a circle around the pole?
I drew a circle around it, and I
It
only
would
got,
be-
I only want this value here.
Yeah, it would be 2 pi I residue that you took half.
Because of the symmetry, right? Imagine that you let that circle get smaller and smaller and smaller. It's gotta have symmetry, right? What do you mean integral of a small circle? This is not, right, remember, we can't do this with just any function.
Yeah,
Right?
We're trying to do the whole thing and we're just gonna call it H1 pi I residue.
Well, depending on the function that we used, right, it's very specific to whether or not it's well behaved here and here. Remember we talked about symmetry? So is it symmetric on the path up and down? If they contribute two different amounts, you definitely cannot just divide by 2. Right? Right, if the symmetry is this way, right? Left and right around the pole, then you're fucked. But if it's top bottom, you're okay. Right? Because then this contributes the same amount that this contributes, and they have to, of course, add to 0. So you have to ask all of those arguments of the function as you go to figure out what that top half is. But you can just in your head, but not in your head, you can kind of like hand wavingly say, look, I don't need to do the integral because I know that if I have these conditions correct, as I make that thing smaller and smaller, it's just enclosing the pole. I know the behavior here, I know the behavior here of the function itself, and I know that they must equal either 0 and or the 2 pi sum of the residence, right? Okay, so then you get the contribution here, and then of course, you go along that whole thing, but you have to subtract off that piece, right? So you're going the opposite direction of the one thought of this, right? Normally the residue of that. Yeah. What?
What do you say?
Okay, so normally, here's the pole, right? Go around it like that, right?
Yeah.
But now look at the arrow.
Ah.
As I go across, I go over. So that is an opposite direction, so it's negative. Right? Paths matter, right? Directions of the paths are really important. Okay, so you might need that too in the homework, I don't know. Okay. Okay, so that was fun, right? We liked this one. This is one, almost everyone's favorite. Let's put a pole at the center. Maybe this is our good old friend 1/z. Okay. And I want to do an integral around the whole thing. Okay. So I want to go here. And now what do?
Do you do 3 1/2 around it?
Yes, we get to build this really fun thing. We. Okay. And maybe we put a little branch cut in here. We want to be specific, right? Okay. That's fine. That's a perfectly good contour that we could use. And so of course the value in here is 0, right? But that takes into account, okay, I subtract off this. What's the contribution from these? These will probably cancel if you did it properly, right? If you used it appropriately, this leg here and this leg here, they're going in opposite directions, right? So as long as you have some symmetry about the x-axis, contributions from those should be 0, right? Similarly, probably just taking this off. Okay, so now a full circle as opposed to a half circle from before, that's okay. Make sense?
Yeah.
Okay, that's a fun one, but it's not as fun as these other ones that I'm about to blow your mind with. Let's move some of these poles, let's make them more pesky. Okay. So let's put some weirdo poles, put a pole here, pull out here. Okay, so I'm gonna throw you, I'm gonna show you 3 complementary contours. Okay.
Like equal?
No, that they complement one another. So they will be related to the ones that we've seen before. We've been fucking with circles. This is not quite a circle, but you'll see that it has some fun relationships to the ones that we have cared about before. Okay, so let's start here at some distance. Call that a distance lambda. I'm gonna go straight up. Okay, and then I'm gonna go around in a semicircle until I get back to here. So imagine that's a circle. I just chopped it.
Why didn't you talk about the word?
What?
Did you talk about the word? I talk about like such a weird spot.
I know.
What?
Okay, why did I chop it at a weird spot?
I knew the answer, I'd tell you.
If you knew the answer, you'd tell me. So remember why we're doing these contour integrations in the first place. As fun as it is to just like fucking do weird shit in math class, sometimes you want to relate the value of your integral in the real or imaginary space to things that you can already calculate easily. What am I doing here?
Area of the circle.
No, look where I am. I'm at some fixed x,
X a constant.
right? It's not the same as the origin, it's at a fixed x,
But it's like a single value of X.
right? But it's a single value of x, right? So now, let's say I have an integral, for example, and I'm just showing you one of these. You can imagine rotating this in your brain, I don't give a shit, right? Let's imagine you want to evaluate something, right? And you want to take the integral this way. So you want this path for some reason. Now you know what its relationship would be to this one, right? And you might be able to do this one more easily, right? Okay?
Yeah.
Okay, but of course, it would then require what?
Some more contours surrounding the.
What?
Some contours surrounding the poles.
Or
No.
this.
No, watch, I'm gonna show you a fun one, right? I'll leave the poles there. Here is your complement. Right? No, hold on, so this is important, right?
Yeah,
Because what are we thinking about here?
well,
We're thinking about if you have that whole circle, you know how to do that integral. And you can break it up on a line into two integrals. Now, the whole circle, by definition, has to be equal to this circle plus that circle, doesn't it?
yeah,
So we can go through and we can piecewise relate the sections of the integral to one another. So that we're really doing algebra as opposed to this integration. And this even includes. I should have done that one first, fuck. This even includes, oh, I'm running out of time. That. What? That's perfectly good integral. What? Oh, yeah, you can make a branch that too. Okay, like I'm laying in bubbles. Does that make sense?
yeah,
So these are all very useful contours that you may or may not need for the rest of your life. That's it.
No.
What that? It's not better, it's just as worse as when I drew them. Okay, cool. Questions about this? Okay, places that you will need contour integration. Louisville theorem, Green's theorem uses that. WKB approximation for quantum mechanics. So graduate school comes up a lot. I would certainly recommend like brushing up on, that before you take your first grad class.
or say
Math methods.
WKB, what is it?
WKB approximation. If you do fluid mechanics and you do any form of conformal mapping, which is where you take one space and you turn it into another space. You're gonna use complex analysis there. What else do you use it for? They love it for proofs. People love it for proofs. Self-similarity solutions, love it there. Quantum mechanics is, you've got the eyes in there already. Anything else? Wave theory. Okay, question before we move back to non-abelian groups. You want non-abelian groups? You want non-abelian groups?
Yeah.
So let's draw our non-abelian triangle. Okay, and see how I drew the triangle originally. All right. Those are the lines of symmetry. And we said that we could think of them in the context of like making markings in each of the corners, right? And we said that for something like the representation of a triangle, that's a pretty abstract object, but we can think of operations that we do to the triangle. You can, you could rotate this triangle like 10 degrees. Right? And that would be not part of the original set. So we can think of orientations or images of this triangle as part of a set, elements of that set. Let's say that it's a finite set. If it had the rotations, then it would be an infinite set. But if it's a finite set, then we can only have maybe this on the bottom, right? This long base on the bottom. And it only the relative orientations of these are what matters. Is that question making sense?
Okay, okay.
Okay, so what are the two rotations that we are permitted to make?
Clockwise and counterclockwise?
We're just gonna treat clockwise as plus, counterclockwise will be negative. But if I want to keep this base here, what are the two rotations that I'm allowed?
Oh, you want to keep the base, I guess rotation with respect to the K.
Yeah, like along the k-axis, like flip it that way.
That is not a rotation.
Oh, that's not a rotation. Oh,
That would be a reflection here. We don't know anything with the three-dimensional world. Okay, this is just a two-dimensional world.
So to keep it where it is, you're allowed 360 and 0?
Well, no, so I want to keep this bottom aligned with the bottom, so I'm not allowed to do this, right? Which would make it like that. I
okay.
need to be able to rotate enough so that the base lays flat. Imagine that it's a child's block in a 2D world. So I can't tilt it so that it's underneath the ground.
You can't rotate it. Okay, so you gotta,
Well, you could rotate it, we'll call that an inversion, but it's not a rotation. Right?
Okay.
Because we don't know about that third axis. It's just a mirror flip.
So you don't want the same symbols in the bottom, you just want it to lay flat?
Right. And we're gonna talk about all of the different things I can do to this triangle. Okay,
okay,
so
okay.
what's the first one? R is
Is it 120?
120, I might call that 2 pi over 3,
Okay.
right? Yeah, I think so, right? The correct.
I don't spend my time rotating triangles.
Well, now you do.
All right. Okay, so that's the rotation.
So you're rotating it like this way is positive, right? Okay.
Yeah, we're gonna imagine that the rotation axis in this 2D world, right? Because we're stuck in the board. All right, what's the other one?
2 times that.
Yeah, 4 pi, 4 pi over 2.
Okay. So that is the first operation I can do on the triangle. Okay, what are the other operations?
Like,
Reflect, yeah, which would be what?
Negative 2 pi over 3.
I don't,
No, that would be rotating the other direction. That's applying the same operation but
Yeah.
backwards.
what do you guys think?
Now, now you're asking for third dimension.
No,
Are you guys think how we reflect it? You guys,
yeah, so reflections don't need a third dimension,
Okay,
right? Because you can see a reflection in a mirror.
reflect over K?
Exactly. So reflect through what line?
okay.
So there is a line of reflection here. This will stay unchanged and these will change, right? So you can have a K reflection, an M reflection, and an L reflection, which reflect through a line of symmetry. We see why that is not a rotation?
I mean, yes, I see why it's not a rotation.
You can think of them the same as rotations, and of course, we're about to show that they are equivalent options, but it's not the same.
Should have been the same but not the same.
Correct. Okay, so let's do a couple things. Some combinations. So these are R prime, K, M, and L. I am going to say are members of the set. What?
Set of operations.
Yeah, are, no, the operation is using them.
It's just like how it was when you were saying.
Yeah.
F,
It's a set
rotation matrix,
with,
What's that?
rotation matrix, sine, cosine.
Yes, yeah, so this is another example, but now we're gonna have triangles so that we're like, oh, I get it now. Right? Okay, so what happens when I apply R twice?
You get R prime,
Correct. What happens when I apply R and R prime,
you get the original cycle.
which is the identity, right? So we need an identity. Okay, good. Let's put that up there too. Don't do shit to my triangle. Right? That's I. Okay. Okay, we're gonna see if we can find any inverses. Okay, so let's show some other ones. What happens if I take K twice?
I,
What does it mean if I do K times K and I get I back?
then
Oh,
it's inverse equals itself.
Yeah, so where we saw that earlier with the modulus one, right? So K equals itself, or sorry, K equals its inverse. Okay, that's good, because that gets all my reflections right away. Maybe with R.
So,
What would I say? Okay, what are the R inverses?
I guess the inverse of R is R prime.
Correct.
Yeah.
Because that takes you back to I, right? And similarly, let's think about the way that we do this. If I go R prime, I get I. If I go R prime R, do I get I?
yeah,
Okay. Do I need to write these down, my losing people?
no, you're following.
Okay,
I mean,
alright. So now let's prove the fun ones. Okay? Let's prove K and M.
What about it?
Let's use K dot M. What do I get?
Oh,
So let's start with this one. Let's apply M to it.
okay,
What do I got?
the top would be this open circle.
The top is open circle.
Top is. We just did K. We just did M.
We're only doing M here.
Only doing M?
X is
Okay.
at the top. Good.
Open, close, or fill.
Good. Okay, now, what's that equal to?
That's the,
Still X at top.
Still X on top?
Yeah, and then flip the bottom.
Okay.
They have fill.
Is that right?
you did M first, yep, and then you did K.
Okay, so what's that equal to?
Not and then.
What?
Not-
Not an identity, good, so we know it's not I. So let's start by saying, okay, so let's say we showed that K circle M gives you this. And that is equivalent to what?
The identity times K.
Our.
So this is our original state, right?
Yeah, that would be,
Oh,
to R.
rotation. It's, R.
Is it? There is no minuses.
Yeah, that would be R.
Nope.
Oh, no,
Wait,
negative
R,
R.
oh, R is wrong.
It's R prime.
R prime, oh,
It is a rotation, but you gotta go farther. Okay, so we just showed that that's R prime.
Yeah,
right? Am I wrong?
I want to rotate the other way for some reason.
You can't, right? We don't know about the other way.
I was.
Okay.
Positive.
Okay, do you wanna do any of the other ones? Alright, let's do MK. Show me what MK is on your own. Oh, fuck, I didn't wanna actually do it. There's money.
MK what we just did.
Yeah, I think.
No, you do it in a different order now.
Yeah.
So K,
M,
Okay,
K.
so when you do KS.
so you do K first and then you apply M.
Yeah, so first apply K and then apply M.
Okay, yeah, then that one, okay, that's the one I did the first time when I got confused, because I was doing it, okay, go on, okay.
It feels like when you put M first, you should do M first, but you do the second one first.
Yeah.
Yeah, so
that's
think
what I
about,
did,
think
yeah.
about it like this. Applying to an object. So
Okay,
this is kind of the way that we use it instead of raw and ket notation in quantum mechanics. Right, is that the relative location acts on a certain object.
it's like matrix operations, they put on the left.
Sure. So what do you get here?
So we flip the entire triangle. Like,
Yeah, here you get on the top, you would have it open, the bottom right, you'd have a sort of the dot, closed dot, and then the left would be the X.
wait, does the entire triangle not flip any sense?
We're flipping over the M.
Yeah, flip over K first,
K,
and then you flip over M,
you said K, flip it like.
Okay.
but not really the same thing.
Okay, so
So you do it.
Same version.
also it's like you're spinning like.
Yeah,
It's a mirror.
Yeah.
Mirrors have lines of symmetry, right?
yeah,
Do they?
planes, or something.
Yeah, they do.
It's not even new yet.
Okay, all right, so what do I end up with? What's the final state here for this
What you
triangle?
said.
Yeah, so the top would be the open circle.
Yeah.
The bottom right would be the closed dot, and the bottom left would be the X.
Okay, and that's equivalent to,
R.
that is just R. Okay, so K dot M was
R
R.
prime.
R prime. So now we understand what it means for a group to be non-abelian. So when we said that we had abelian groups before, we didn't care whether it was 1 times 4 or 4 times 1 under the operation multiplication modulo 8, right? Because we just got back to the same thing. Now, the order of the multiplication matters. So even though it's associative, right?
It's not commutative.
It's not, it's a non-abelian group.
No, okay, no.
So abelian means the property of the individual multiplications here don't matter. Wait, abelian means, yeah, abelian means they don't matter.
So it's because the order changes that makes it not abelian.
And that's different from our associative property earlier. Right, because we had 1, 2, 3 equals 3, 2, 1. Does that make sense? Okay. All right. So you can build up a multiplication table of this set. Do you want to see it?
Yes.
You want to build it yourself? You want to see it? No, you don't want to. Okay.
No.
No. All right, so let's do the set, of course, is I, R, R prime, K, L, M. I, R, R prime, K, L, M. This is a bigger multiplication table than you've seen before, but no one's worried, right? All right, what's in the diagonal?
Just I.
And
I are.
the true?
They're all their own inverses. Yeah.
No, not, is it R, not R.
All the reflections are their own inverse.
Yeah, the reflection, yeah.
Interesting.
And yeah, so the rotations are fine. Make them eyes.
The rotations are fine?
Wait, no, they're not.
Yeah,
No,
The
remember that,
reflections are eyes and the
Remember that these are the operations together. So it's I times R. What do you end up with?
R,
Which ones are going first?
I'm talking about the diagonal.
oh,
No.
so R times R is R prime.
R times R is R prime.
Yeah,
Good.
that's true.
R prime times R prime. R, good. Okay, now K times K.
I,
There we go. L times L. M times M. Good.
uh,
That was rough. Okay, now let's go along this line. This one's fine. What'd you guys get here?
oh, R prime,
Good, and then this one. Okay, interesting, interesting. So far it's Sudoku like. You think it's gonna be Sudoku the whole way through? No. Okay, what about the next one? What is R with R prime?
I,
Okay. Or R with K. What do you say?
I,
That's what I'm saying, is it depends on the order, which one goes first, which one goes
Do we
second.
have any of them?
well, we had those.
We have M with K, right? Shit. All right, M with K is what?
R,
M with K was R.
And then K with M is R prime.
K, M. Should I just do the rest? Yes. All right. This first one is M, K, L. The second one is L, M, K. This one here. L, M. Skip the I, R. This one here. M, K, R prime, R. This one here is K, L, R, R prime. Now tell me that's not cool, right?
Yeah.
Notice anything?
no patterns.
No patterns but Sudoku? Okay, so Sudoku is an important pattern, right?
It is, yeah.
It's not symmetric upon the leading diagonal, right? But are there places where it's symmetric?
There are some symmetries.
Yeah. So there's symmetry within what?
Box,
What do you mean a box?
Like little sections, like.
like, 3x3 in the top left,
Yeah,
that's like what you.
okay, hold on, so is that symmetric? It's symmetric that way. Good, and what about the one next to it?
It makes like a, it's like, no, it's like that.
Alright, so this one here is what you were talking about before,
Yeah.
and this one here.
On the upper,
Oh, shit. Okay, what about this one?
M, on the bearing.
Oh,
Yeah,
Here?
yeah. No, the other way,
Right.
Oh, okay, interesting, and this one here?
the I.
I'm gonna make it be inside.
And let's see who's in each box. Here's your KLMs. Here's your KLMs. Here's your RI R primes, and here's your RI R primes. What the fuck? Okay. So these group multiplication tables, you know, they have some really sort of tricky, fun backstories to them that speak about the nature of something as simple as doing a reflection or a rotation of the triangle. We won't get to the place that this could be used, but
You could look at 2x2 matrices, and this would give you similar types of rotations.
Oh,
Rotations of 2x2 matrices. If you like this stuff, take the group theory class that math offers. It's fun. If you like particle physics, I would recommend at least picking up a book on group theory. Quantum mechanics at this level, at your undergraduate level, won't go easier for you if you know group theory, but at the graduate level, it might. Questions, comments, concerns?
Thanks.